Today we are going to learn how the frequency of probe is selected in ultrasonic testing. Okay, we will go and read word by word. The following section is from the IAEA UT textbook. Okay, we'll see. The selection of the frequency depends on three things. Okay, one is the size of the smallest flaw that is to be detected. Second one is the crystalline structure of the specimen, and third one is the degree of the absorption of the specimen offers to the ultrasonic beam. First we'll see what is first factor. What is the smallest defect you want to find? Like smallest flaw you want to detect. You want to detect. Okay, what is second one? Crystalline structure, like crystalline structure. Okay, and what is third one? Absorption of specimen. You understand, right? Absorption of specimen. Okay, see, the first consideration calls for the use of as high as frequency as possible, because what it says that if you want to find the smallest defect, okay, you see, normally defect size in the size of the defect, size of the flaw you can detect in ultrasonic inspection is considered as lambda by 3. This is of this order. Okay, now if you see you want a smallest flaw and they are telling that this is the flaw you can detect in the UT, right? You see that frequency and V is equal to nu lambda. Okay, you can say f lambda. If frequency is more, then lambda is less. That means if you want very small flaw to detect, that means lambda should be very less. That means lambda by 3 should be very less. That means lambda should be less. That means frequency should be very high. So it is demanding high frequency probe, right? High frequency probe. You see, the first consideration calls for the use of as high as frequency as possible, because generally the diameter of the smallest detectable flaw is equal to or greater than a third of the wavelength of the ultrasonic waves used. Flaw equal to or greater than a third of a wavelength of, sorry, this is this symbol. Okay, this symbol. Okay, wavelength used. Thus, the greater the frequency of the ultrasonic waves, that means if you are increasing the frequency, then lambda will be very less. Thus, the greater the frequency of the ultrasonic waves, the shorter is the wavelength. And hence the smaller is the diameter of the smallest detectable flaw. In other words, the sensitivity of the flaw detector is better. You understand, right? If you want the smallest flaw, lambda by 3 should be very less. If lambda is very less, frequency is very high. That means if you want smallest flaw, you need to increase the frequency to very high. Okay, we will see second consideration. Another additional advantage in the use of higher frequencies, if you're using higher frequency, is that high frequency probe, this is very important point, high frequency probes, what it does, emits shorter ultrasonic pulses. Okay, shorter ultrasonic pulses. That implies you get better resolution, right? Better resolution. You understand, right? Okay. Then, so two considerations require the use of low frequency probes. what are those two considerations? Here up to now we have talked about high frequency probes. Here they are telling low frequency probes. What are those two considerations? Require the use of low frequency probes, namely if the grain size or the absorption of the specimen is large. That means they are talking about these two parameters: grain size or the absorption of specimen is large. Grain size is large or absorption is large. Okay. Larger grain size in a specimen cause scattering if in the material the grain size is large. Okay, grain size is large, it causes grain size. If it increases, that implies scattering increases, okay, which cause scattering of the ultrasonic waves, which results in a lower depth of penetration of the ultrasonic waves. If scattering increases, that implies depth of penetration decreases. Lower depth of penetration ultrasonic waves, lower flash detection sensitivity, and also the display of the considerable grains or structural noise indications on the CRT screen. That implies, see, now you see that if grain size is increasing, that means scattering will increase. Okay, if scattering is increasing, the ultrasonic sound will not go up to the depth of the material. The energy will get completely dissipated at the half of the depth or somewhere else. So the depth is the ultrasonic sound is not going into deep into the object. If it is not going deep into the object, much of the area is uncovered. That means sensitivity decreases. Okay, and also if grain size increases, scattering increases. Due to this scattering, noise increases. Okay, considerable structural noise. So noise also increases. Okay, noise increases. Now if you see the next explanation, this display of grass on the CRT screen makes the differentiation of small flower echoes from the grass difficult, if not impossible. You see, normally there will be some grass, okay, and there will be some grass, okay, and if the echo height is of also very small height, echo height is of also very small height, these are the grass. And if it is echo of small height, you cannot differentiate between the grass. Okay, this is grass, this is echo, you cannot differentiate between both two, so it is also becomes difficult. Okay, now the absorption of the ultrasonic waves in a specimen increases with the increase in frequency. Here they are telling is a third consideration. If frequency increases, that implies absorption increases. We will see why. Absorption increases. Using a high frequency probe to test a high absorption specimen results in a lower penetration range and lower flaw detection range. They are telling that frequency, if frequency increases, absorption increases. If absorption is getting increased, the ultrasonic energy will not go deep into it. So what you are getting it? So penetration is very less. Penetration less, and that penetration less means that implies flaw detection less. That means sensitivity decreases. Okay. Now you see, we have discussed 3 points. We will see that as a result of the above discussion, the following general rule for the choice of test frequency may be adopted. The frequency should be as high as possible. They are telling that frequency should be as high as possible, but the upper limit is set by the grain size and absorption of the test specimen. So the upper limit is set by limit set by grain size and absorption, right? Okay, usually forged materials are examined with the frequencies. So they are telling forgings are examined with the frequency between 2 to 6, while cast specimens, so cast materials specimens with a coarser structure need frequency. If it is coarse grain, so frequency 0.5 to 2 megahertz. Okay, ceramics, example of electrical insulators, also present good ultrasonic conductivity and can be tested in most cases with the frequency 2 to 4. Okay, synthetic materials can be tested with a frequency from 1 to 4 megahertz according to their absorption thickness. Okay, the test frequencies for concrete and similar other materials. You see, if we can, they are telling that, see, forgings, castings, cast, ceramics, and then synthetics, right? They are telling that forgings 2 to 6, castings if it is coarser 0.5 to 2 megahertz, ceramics 2 to 4, synthetics 1 to 4. Okay, the test frequencies for concrete, okay, you see, concrete and similar materials 50 to 200 kilohertz, right? So they need special flaw detectors. Once we will revise all the topics. Okay, once we will revise. Okay, while considering the probe frequency, they consider 3 points. One is smallest flaw you want to detect, and crystalline structure, and absorption of the specimen. You see, if you want, and in UT there is a thumb rule that the smallest flaw that can be detected is more than the lambda by 3. Okay, so you see that lambda is a wavelength. This is the smallest flaw dimension. Okay, so lambda by 3. So here it is saying that you want the smallest flaw. That means lambda by 3 is very small. That is, lambda is very small. If lambda is very small, frequency is very high. That means you need a high frequency probe for the smallest flaw. But if you see crystalline structure, if the grains of the structure is very large, then the scattering is getting, then the scattering increases. If scattering increases, much of the energy will not go dissipate at the initial stages itself. It will not go to the depth of the block. So depth of penetration decreases. If depth of the penetration decreases, that means much of the area is uncovered. That means sensitivity is getting decreased. And also, as scattering increases, noise increases. Okay, this is the second consideration. Okay, now third consideration. You see that this relation you need to remember. If frequency increases, absorption increases. If absorption increases, then penetration decreases. If penetration is decreasing, sensitivity decreases. Okay, so now you see one thing, that is the smallest flaw thing is demanding higher frequency, but the remaining, that is crystalline structure and the um, crystalline structure and the absorption factors are demanding low frequency. But so you need to do a balance between these two things. So how you do, you see, you use as high frequency as possible, but this limit, upper limit, is set by grain size and absorption. If grain size is more, like you see in the cast, this is coarser, right? Grain size is more, so you are using less frequency. Okay, and then also, okay, and also if absorption is more, use the less frequency. You understand, right? Use as high frequency as possible, but upper limit is set by the grain size and absorption, right? Please guys subscribe to my channel.